Okay, so in this video we're going to do a few more examples of solving differential equations using the Laplace transform method. So as we've seen in previous videos, the first thing we do is we translate the differential equation into an algebraic equation using the Laplace transform. So we'll just write down a few things here that we're going to be using. So we're going to send both sides of this. Now here we started with x, so we started with a function of x, and the Laplace transform will take theta as a function of x to theta as a function of s. Well, big theta as a function of s. Now rather than writing a big theta, there is such a thing, we'll use a big T. So we go from theta of x to big T of s, and that's what the Laplace transform is doing. And the other things we could write down at this point, so we know theta of x is going to be sent to big T of s. We may as well write down that this is a constant, so a constant a is going to be sent to, by the Laplace transform, constant over s. And the other formula that's relevant here is what happens to a second derivative. So the formula that you see in your big tables is that the second derivative of a function is sent to, and this is in the tables, s squared big F of s minus s times little f of 0 minus f dashed of 0. So these are what we're going to use down here. So you do the Laplace transform on both sides. Linear means that if it's a sum like this, you can do term by term fixing constants. Now this is a constant on its own, you don't really need to fix that. But the minus 0.01 is a constant that you can fix, and then you'll hit it term by term. And here I just write the second derivative as theta double dash, just to put it in this kind of a form. So let's apply this. So the second derivative, now this is going to be similar. Now instead of t we have x, but you always go to s, so the s's are fine. Now this should be little f, big F, little theta. You'd write big theta, but we're going to use big T instead. So this is going to be big T of s, and then instead of f's we're going to have thetas. So the Laplace transform of the second derivative of theta respect to x will be something like this: s squared, rather than big F of s, big T of s, minus s times, instead of little f of 0, it'll be little theta of 0, minus theta dashed of 0. So that's sending the second derivative, minus, fix the constant, minus 0.01, and little theta of x goes to big T of s, equal to, and then we've got minus 0.2, well that's a constant, that'll go to a constant over s, minus 0.2 divided by s. Okay. So that's the first step, do the Laplace transform on both sides, and now what we have to do is solve this for big T of s. The first thing you want to do is apply the initial conditions, and the initial conditions will be in the question, and we'll see them here, that little theta of 0 is 40, so this is going to be 40, and theta dashed of 0 is 0. So we're going to do this on the next page. So the initial conditions say that we have s squared big T of s as before. We've got minus s times theta of 0, that's on the previous page, theta of 0 is in the question as 40, minus theta dashed of 0, which is on the previous page is 0, minus 0.01 big T of s equal to minus 0.2 divided by s. At this point, it's probably worth pointing out a difference between this chapter 3 and chapter 2. In chapter 2, you can find the general solution that doesn't depend on the initial conditions, so with the a and the b. Here, in that chapter 2, you find the a and the b at the end. In this chapter, you kind of find the a and the b in the middle, like there's going to be no a and b here. Okay. Anyway, so now we're going to solve this for t of s. Now you're looking at this now as an algebra problem, which is supposed to be easy. You want to get all the t of s's on one side. This thing is missing, so we're going to add, or this is not missing, it's in the way. We're going to add 40s to both sides. S by 40 is 40s, so plus 40s to both sides. And then what do we have? S squared times t of s minus 0.01 big T of s equal to 40s minus 0.2 divided by s. Okay. Now we've seen in previous questions, and you'll start to get used to this in using the Laplace transform method, that when you get down to here, when you have all your t of s's on one side, you need to take out the t of s as a common factor. Now this particular question, we're just kind of flying away, but this question was broken up into two pieces. The first was to find t of s, and there's a formula for t of s on the previous page, so we'll try and go towards that and see how we get on. The next thing to find t of s is to divide both sides by s squared minus 0.01, so we'll do that here. So we're dividing both sides by s squared minus 0.01. And what we said before, if you're dividing a sum by something, you divide both of them. And if you've got 0.2 divided by s and also divided by this, it'll look like this. Okay. Now what we might do is we might have a look at the answer for a second and compare, because we're actually not that far away. So if we look at the answer, this is on the previous page, we're looking for 40s squared minus 0.2 divided by s by this stuff. Now I'm not as concerned about this. We want to get a single fraction is the big story, and at the moment we don't actually have a single fraction. So well, what you need to write to add fractions together is you need a common denominator. Now what you could use is s times this, so this side here is missing an s and an s. Now you have a common denominator, you can add them together, and you have 40s, which is 40s squared, divided by s times s squared minus 0.01. Okay, and this is good. Now the question is coming up at the end, how do you factorize s squared minus 0.01? And it's not necessarily that easy, and it was probably well, it isn't that hard. We'll just take it on a separate page here. So, how to factorize s squared minus 0.01. Okay, so we'll look at a number of ways of doing this. The AC method is a little bit difficult here. Technically it is possible, but it's not really going to work for us. So what we could do instead is use the factor theorem, which says that k a root, that means that if k is a number you put into this and you get 0, that automatically gives you a factor. S minus k, a factor. And if you find the two roots of this, you have the two factors. So that's one approach. So root is this equal to 0, so therefore you look at s squared minus 0.01 equal to 0. And then what you do, well, you're solving this for s, you could add 0.01 to both sides. And you end up with s squared is equal to 0.01. Now at this point, you just have to be careful to note that there are two solutions, there are two roots, because it's very easy here to end up with one of them and not the other. So you look at the square there, and the inverse of the square is square root, so you apply square root to both sides. And here's the problem, we've only got one solution, and this is where you need to be careful. You have to realize there are two solutions, plus or minus this. You go into the calculator if you want, and you get plus or minus 0.1. So what this means is s minus 0.1 a factor, and s minus minus 0.1, which is s plus 0.1 a factor. And then because it's s squared, if you multiply these together, this will have to be it. So this uses a fair bit of theory. Well, it uses the factor theorem. It is actually a much easier approach though. Whenever you see s squared minus something, say s squared minus a, or maybe s squared minus k would be better, but anyway, s squared minus a, this can always be written as the difference of two squares, because anything positive, a here would have to be positive, can be written as square root squared. So this is s squared minus square root of a squared. And then we use the following identity. Now this is something that I would say that you either remember it or you don't know. I mean, it's something that you would have seen all the way through school and in CIT as well, and it is that the difference of two squares, x squared minus y squared, factors as x minus y times x plus y. And in particular, therefore, if you're talking s squared minus a, which is s squared minus root a squared, we can factorize it using this identity. Identity means that it's equal for all values of x and y, in particular s and root a. So you get s minus root a, s plus root a. And you can always factorize s squared minus a like that. So in our particular example, we're looking at s squared minus 0.01 is equal to s squared minus the square root of 0.01 squared, which is equal to, now you can do the square root of this on your calculator or whatever, and you get 0.1. So it's s squared minus 0.1 squared, and it'll be using this identity, s minus 0.1 times s plus 0.1. And personally, that's you'd hope to recognize this as a square straight away. It's 1/100th, which is the square of 1/10. So you end up with this thing here. So this is where, however you do it, there's various different ways you end up. This is called the difference of two squares. So that's how you factorize the s squared minus 0.01. So that's all that's left here. So you have to kind of recognize this ultimately as s squared minus 0.1 squared and use difference of two squares. So we have that t of s, the answer that we were supposed to find, which is 40s squared minus 0.2 divided by s, and now s squared minus 0.01 is s squared minus 0.1 squared, which is s minus 0.1 s plus 0.1. Good. Okay. So that's the first part of the question, and the second part of the question is to go back from t of s back to theta of x. So that's what we have to do next. So you're looking in the tables now. The relevant things in the table is a constant over s goes back to a constant, and the other relevant thing is that 1 over s, we'll write it like this, plus a goes back to e to the minus at. And the way it works is if this thing is minus, this thing is plus. So it's like if it's plus, it goes back to minus. If it's minus, it goes back to plus. This squiggly bit shouldn't really be there. Right. But as usual, everything is squashed together, which is not what you want. So what you're going to need here is to write this complicated thing as a sum of simple terms. And writing something complicated as a sum of simple terms is doing the partial fraction expansion. I've seen this many times, and the first step is to factorize the bottom. Luckily, the bottom is factorized by us already, and we asked for the rules, and this is a rule 1, this is a rule 1, and the s looks a bit different, but it's just like s plus 0, it's also rule 1. And when you've got all rule 1s, you're delighted, because what that means is you can do the cover-up method and do this kind of quickly. So the cover-up method, let's look at this. So we got 40s squared minus 0.2s divided by s times s minus 0.1 times s plus 0.1 is going to be something over s plus something over s minus 0.1 plus something over s plus 0.1. Okay, so how does this work? Well, again, this cover-up method says, okay, so we'll do this one first. This is probably the easiest one. So the cover-up method says, okay, to find out what constant goes here, you're gonna cover this up over here, say like that, and what you're going to put into everything that's left is the value of s that makes this thing equal to 0. So we're hoping to substitute something into 40s squared minus, now I've added in a 0.2s, but that actually isn't there, so minus 0.2. I've got an s over here, I'm going to sub something in there, and then an s plus 0.1, I'm going to substitute something in there. And the question is, what value of s makes s minus 0.1 equal to 0? It's s equal to 0.1. I can find out in a moment on the calculator what that is. Now the next one we'll look at is s plus 0.1. So again, you cover this up, and you're going to put the s into everything that's left over. So what's left over is 40s squared minus 0.2 s times s minus 0.1. And the question is, what value of s makes s plus 0.1 equal to 0? Solve that equal to 0, you get minus 0.1. So this is minus 0.1, minus 0.1, minus 0.1. And then the last one, which is actually the easiest, but it's a little bit cheeky, cover up the s to find out what, I'll cover it for me, to find out what goes here. So you're talking 40s squared minus 0.2 divided by s minus 0.1, s plus 0.1. And the question is, what value of s makes s equal to 0? The answer is s equal to 0. So you put in 0, 0, 0. Okay, now we can find out what these things are on the calculator. So the first one is minus 0.2. I don't put in 0 squared, that's just 0. And on the bottom I have minus 0.01. So this gives me 20. Just want to check that. Yeah, 20 divided by s. The next one, let's see. 40 times 0.1 squared minus 0.2 divided by 0.1 times 0.2. This gives me 10. And then the last one, so I'm just changing some signs on the calculator here. And it also comes out to be 10. Hopefully I haven't made any stupid mistake here. Quick look suggests I'm good. Okay, and this can be sent back easily. Now, just be careful, you're not going back to t as usual, you're going back to x. So when you use the tables backwards, rather than going back to t's, you go back to x's. Okay, so let's send this thing back. Theta of x. So do term by term fixing constants. So fix the 20. Well, 20 over s is constant over s, goes back to constant over s goes back to the constants, just 20. Fix the 10. 1 over, now we'll do this last one first because this one is easier. So fix the 10. 1 over s plus, it's written up here, 1 over s plus a goes back to e to the minus at. So this would be e to the minus 0.1t. Hopefully we can see everything I'm writing. And then this one, if it's a minus, it'll come back as a plus. And to see that, you can do minus minus if necessary, but if it's a minus, it'll go back to a plus. So this is e to the plus 0.1. And of course I made a mistake myself here. This should be x, not t. Okay, and that's basically it. Now we can just make maybe one short comment on the solution here. So usually you're going to see s plus going back to e to the negative, because if usually we're interested in the variable in the first domain not being x, which is a distance, but t, which is time. And usually we might be interested in time getting very, very big. And as if instead of x here we had t and time got big, this thing will go to infinity. And usually in any kind of physical system you won't see infinities like this, something getting very, very big. Now it does happen here though, because x is actually the distance along a rod, which is finite. So like x gets has a kind of a maximum value, and so this doesn't go infinite. Okay, so that's one example there.